Shende, University of Oregon, USA. Professor Aritra Bandyopadhyay will moderate the session. Without any further delay, I hand over the session to Professor Aritra Bandyopadhyay. Thank you. Aritra sir, please.
Thank you very much for inviting me today. I hope you can hear me properly.
Yes, sir.
Yeah. Okay,
Aritra sir, please. Aritra sir.
Can you see my slides properly?
Yes, sir. Slides are visible.
Okay, great. So thanks again for inviting me today. I'll be talking about supercomputing, accelerating research and development for startups. And let me give you a little background about myself. After graduating with my BTech, I joined Tata Unisys Limited and was stationed in CDAC, Pune, where I worked on the Param project way back in 91 to 94. And then I went on to do my MS and PhD at the University of Oregon, doing internships at the Los Alamos National Laboratory, working on HPC projects. And now I serve as a research professor at the University of Oregon, and also the president and director of Paratools Inc. in the US and Paratools SAS in France, a spin-off of the University of Oregon. I also hold a joint appointment at the Argonne National Laboratory, and I serve as a member of the Department of Energy's Advanced Scientific Computing Advisory Committee and lead the E4S and the Tau Performance System projects. So starting a business is always risky. There are many issues that you have to face, whether it's financing, the technology trends, and financing may be one of the most important issues as you take the steps. You may be wondering about how to use bootstrap the operation. You may have to take loans from family, friends, banks, whether they are interest-free or with interest. That can make a big difference. There may be angel investors that you are talking to or venture capital folks. But one of the best advice I got was that instead of looking for investment and taking away your equity, you should be looking for paying customers. Are you trying to solve a problem that others are interested in? And who are your potential customers? You may get support from the government to develop the technology. And in many cases, you don't need to part with your equity in the company. There is the Small Business Innovation Research Program in the US that seeds such technology with grants. And there may be similar government-aided programs that you may want to look into. And some entrepreneurs don't necessarily give up their day jobs as they start their first business, because it takes some time to launch the product. But you need to keep your focus on what problem are you trying to address with your startup. So the issue that we were looking at is that as our software gets more complex, it's now getting harder and harder to install the AI/ML, electronic design automation, and HPC tools and libraries correctly in an integrated and interoperable software stack.
I'm audible?
Yes, you are audible.
Okay.
And it's harder to install our applications on bare metal HPC systems and on cloud platforms. And with growing hardware complexity, it's getting harder to even accurately measure and optimize the performance of our workloads. And to address these two problems, we have the Tau performance system that aims to deliver a scalable, portable performance evaluation toolkit for both HPC and AI workloads. This is a project that grew out of my PhD dissertation work at the University of Oregon. And Tau can be downloaded from this URL. And the second project is the Extreme Scale Scientific Software Stack, or E4S. There are 4 S's in this acronym. And there we are developing a full stack of HPC and AI/ML tools to lower the barrier for entry. It includes Tau, it includes a large number of tools that I'll describe, and it is now available through our startup company on cloud platforms. You can download E4S with containers right from this e4s.io webpage, and it's available for free on this web page where you can generate your own workflows on your own hardware and deploy these containers. The Tau performance system supports not only CPUs, but also GPUs. GPUs from NVIDIA, AMD, and Intel. And it has instrumentation support for observing the performance of your application that may use a number of different runtimes, such as MPI, CUDA, ROCm, DPC++, even OpenCL and OpenMP using OpenMP target offload directives. And we support a number of different languages, the standard C, C++, Fortran, Python. We can access hardware performance counter data. We support many different instrumentation interfaces, including perf stubs, CAM timers, COCOS, and many other runtime library hooks. The key thing to take away is that you want to measure the performance of your application. Using Tau, you do not need to change anything in your source code. You do not need to change anything in your runtime systems. You do not need to change anything in your binary. Your unmodified binary can be launched using a tool called Tau exec. And then it can generate profile files, traces, and you can analyze the data using a number of different tools. So instrumentation is supported for different languages at different levels, and those hooks then create the measurement. They call the timing libraries, and you can generate profile files, traces, and then analyze the data in tools like Paraprof, Perf Explorer, or Vampier from TU Dresden, and Perfetto.dev. So in case you're wondering, what can we use Tau for? Tau can show you how much time is being spent in different code regions in your application, be they at the routine level, at the outer loop level. Even within the loop, you can see the contribution of each statement and how much time is being spent in OpenMP loops, in kernels running on GPUs, data transfers between host and devices. You can see, instead of wall clock time, how many instructions are executed in different code regions. So we have support for PAPI and Liquid hardware performance counter libraries. And you can then see things such as floating point instructions, branches taken, level 1 data cache misses, etc. You can also find out, while running a message passing interface library program, how much time your application spent waiting for other processes to catch up at a barrier, a synchronization barrier point within a collective operation. So if you are doing a broadcast operation using MPI, you could see how long the application spent waiting in each process at that collective sync operation. You can see the memory usage of your code, the footprint of your application, and by the memory footprint, I mean the sum total of the total memory being used in the process at any point, which includes the stack, the heap, the data, the text, the BSS, and the total high water mark of the memory usage. You can see energy consumption, IO characteristics, which files did my application access, what was the peak read and write bandwidth, what is the total volume of data transferred, how does my application scale. But to do all of this, you need to insert hooks in your code. While we do support a compiler-based instrumentation, a source instrumentation using a preprocessor with a selective instrumentation filter file, the interesting option is to use Tau's dynamic shared object and preload it using this Tau exec app. So if your application is launched using MPI run, then you just say, instead of MPI run application, you can just say MPI run Tau exec application, and then it will generate the profile files for you. You can generate profiles which show you the summary statistics, cumulative statistics of code regions and how much time is being spent, or you can generate traces. Along a timeline, you can view in trace files what each process was doing, how messages were transmitted from one process to another. You can see the temporal variation of your application. So both profiling and tracing options are available with Profiling, you can see inclusive time. That's the total time taken in your application, in the .tau application and all the different code regions. This is an instrumented application. It's using Fortran in this case. You can see loop level data. You can see functions in the exclusive time. You can see along a timeline what each process was doing and how messages are being sent from one process to another. There is a trace visualizer called JumpShot that comes from Argonne National Labs, and it ships with Tau. You can also use the Chrome browser that's already there on your laptops. And this is the same Chrome browser that can load the trace files that need to be merged and converted into the JSON file format. But a better option for using the JSON files, the trace files, is the perfecto.dev. Perfecto.dev is a website. This is created by Google, and it's a trace visualizer where you can load the JSON file that you just created using Tau and then view what each individual process was doing within that process, each thread of execution. And here you can see a GPU thread and a CPU thread and see the flame graph where you can see the level of nesting of all the functions along a timeline. So you can see what your process was doing at different points in time, where the level of nesting was, and what the GPU was doing while the CPU was doing this operation. We also have support for open trace format OTF2 from in Tau, which can be visualized using the Vampire trace visualizer. Vampire is a commercial trace visualizer that comes from TU Dresden in Germany. Here we show you the details about what's happening with the Cocos runtime, and you can see how you can express parallelism in your code using the Cocos parallel for, parallel scan, parallel reduce operations, where you don't know where it will execute when you write the program, but you write it in a performance portable way. Then you configure Cocos to target either a CPU with OpenMP or GPUs from Intel, NVIDIA, AMD, and then the performance portable code can then spawn the kernels and run those on GPU. Without changing the source code, you can target multiple GPUs using the Cocos library. And Cocos is a Linux Foundation project originally developed from Sandia National Labs in the US. And you can then view the performance of your code running on GPUs and CPUs. Again, no, you don't need to change anything in your application. You just launch it with tau exec command and then give it some parameters. Now, tau exec is a very interesting tool. You can launch an application using tau, and then it can intercept the runtime system calls and then substitute one of the libraries with an instrumented version. It can insert tau hooks in your code. You can observe the performance of OpenMP, IO, memory, and even enable other options in tau, such as generating a communication matrix display, enabling event-based sampling, generating OTF2 traces. And this is how it works. If you have an MPI program that you're running on, say, 256 processes, then you can simply change the MPI run command to insert tau exec. If you're using NVIDIA GPUs, you can say enable CUPT or the CUDA profiling tools interface to observe the timings of kernels that run on NVIDIA GPUs using CUDA. You can enable unified memory. If you're using AMD GPUs, you can use ROCm option, or for Intel, you can enable level 0. We also support OpenCL and OpenACC options for runtimes and enable IO profiling, OpenMP tools interface, even memory leak detection, and event-based sampling where your program can be interrupted periodically and you can generate a profile file that contains information at the statement level, which says this is how much time this statement took by enabling event-based sampling. And to turn on support for hardware performance counters, you can use a tau metrics environment variable. There are many other environment variables in tau. We can show you those details later. But once you generate the data, you can launch the Paraprof tool and view the MPI ranks. You can see what each rank was doing, and this is cumulative time, not a timeline. And when you can unstack the bars together, you can see what each process was doing, and then even turn on other options, view the details in, say, a thread statistics table. A thread statistics table looks like this for a given node. It will show you the top level tau application. It will show you the inclusive time, the number of calls. And if you see the context summary, you can see the code regions and how many samples were collected over here, 288 in this case. And then you can see MPI performance. You can expand this tree by simply clicking on it, and you'll see that it shows that at this file, in this function called bin vcrhs underscore, at line number 228, it collected 14 samples. And so it says it took 0.14 seconds in that particular code region. So you can see line by line how much time was spent in each function. And you can see in a context event window, the data transfers between the host and the GPU along a given call path. And we support Python instrumentation. So instead of using Python to launch your application, you can say tau Python to launch it, and then you will be able to see the details of CUDA, the Python code regions, and also data transfers where you can see minimum, maximum, mean values, the number of samples, and the total data transfer along a given call path. Now, call path profiling is very interesting. You can use it to identify where the application was calling what other routine. You can also use sampling to look inside vendor libraries. This is a very interesting case because there are libraries for which you do not have source code, but you can still see what it was doing. In this case, this is a vendor library from IBM running on a Power 9 system where you are using the spectrum scale MPI or the message passing interface library, and you're doing a broadcast operation. So you can see exactly what the MPI bcast function calls internally. You can look at the pthread spin lock, you can see the PAMI calls, even memory copies, and how much time was being spent in these calls along with your Python routines. You can also, when you get a sample, you can unwind a call stack all the way up, and you can see the tau EBS unwind parameter that will allow you to unwind a call stack and see the details of what's happening when you receive a sample. Here is an example of identifying MPI collective sync time, or the time that we are wasting, using the thread call path relations window in tau. So just to get a sense for this, there was no change to the application. We used the MPI library, and we see over here that 574 seconds were wasted in a barrier call on rank number 118 in this code. Now that's a lot of time being wasted. You want to find out where was this time coming from. And you can see over here that MPI all reduce accounted for 382 seconds out of the 574 seconds of time wasted in the barrier. You can see 68 seconds were spent in MPI barrier when MPI reduce was called, or 89 seconds were contributed to the wait in barrier from MPI bcast. So this timer and its immediate parents, timer being shown in the arrow, and you can also see immediate parents and immediate children. Here is a COCOS parallel for call, and this is the first parameter given to the parallel for, which is useful to the application developer. And you can see that detail information using the profile data. So in short, what am I seeing here? I'm seeing how much time I wasted. How much time I wasted in a barrier that I did not call. A barrier that was implicit in the MPI all reduce operation that my program was using. And again, I just launched the application using tau exec, and I get this level of detail that can help me pinpoint the performance problems in my code. There are other AI/ML applications that you may be using. You can use sampling, and you can then see exactly how much time was being spent in the internal functions, like in this case, an eigensolver. You can use call site profiling to partition the time spent in a given call along its location in the call site. So here, it's showing me that when I enable tau call site equals 1, if 14.6 seconds were spent in MPI receive, then in function exchange1, in exchange1.f file at line 68, there was an MPI receive call site where it accounted for 12.6 seconds of time along this particular call site across all the invocations. And in the same file, mind you, in the same file and same function, MPI receive, the same function was called at line 86. So there are two distinct call sites. It's saying 14.6 seconds was spent in receive. At line 68, it accounted for 12.6 seconds. At line 86, it accounted for 2 seconds. So now I can partition the time of a particular call and drill down and see where that call was being called from by just simply enabling this call site like this. We can access IO profiles for a file. We can see exactly how much time was spent in read and write operations. You can see the write bandwidth, read bandwidth. You can see the total volume of data written to each file using tau exec with the IO option. And we also have a 3D profile browser integrated in tau. So you can see along one dimension, the MPI ranks, the threads. Along one dimension, you can see the functions. And then you can see here that this is concave, this is convex. They both add up to a constant. You can move the function and thread slider, and where it intersects, you can see the exact value of the particular rank and this thread. In this case, you see there's only one rank, 199, that has a peak, while other ranks are doing something else. And this is a simulation of a tokamak reactor. A reactor is shaped like a cylinder, and the CPU that gets the central axis of the cylinder has to do more work. And so that CPU is showing up over here in this thread 199, and you can see exactly which loop it came from. So this 3D view, which you can rotate, is a very intuitive view where you can see the shape of the performance of the entire application. You can move the function and thread sliders, and where they intersect, you can see the height and color value, which you can again configure from a list. We also have 3D communication displays where you can see how much communication happened between a sender and a receiver and see where they intersect. You can see the value of the max message size or the message volume in this 3D display. So essentially, you can run your code with tau exec with just the EBS parameter, and it will show you at what line, in which file, in which function, how much time was spent across all the application functions in all the different MPI ranks. And this is just an uninstrumented application. Now we support MPI, we support pthreads, we support OpenMP, OpenACC, OpenCL, even GPU runtimes from Intel, NVIDIA, AMD, Cocos, and Python, and none of them require any changes to your application binary or the Python files. You can also mix and match these runtimes and say, I want to use a runtime with Cocos and pthreads and MPI, and then set the environment variables to enable different options. These could be generating trace files, call path profiles, checking the memory footprint, tracking the power, generating communication matrix, generating call sites, or enabling access to hardware counters. And there are many options. I'll not go into the details of this. There are memory debugging options. The idea is you can just simply launch an application with Tau exec. Then you can even install Tau on your own laptops and then view the profile data in the 3D profile browser in this manner. Or you can do this remotely. But Tau is a tool that has been integrated in a bigger project, which is known as the Extreme Scale Scientific Software Stack. The E4S is a project that came from the Exascale Computing project. And the Exascale Computing project was responsible for creating the largest supercomputers in the world. Its follow-on project is known as the PESO project from the Department of Energy in the US. And you can see that E4S and SPAC are the two projects deliverables from the PESO products. And Mike Heru is the PI of the PESO project. Now, E4S is part of the High Performance Software Foundation, and this includes members from the Department of Energy, such as Lawrence Livermore National Lab, Sandia, Argonne. It includes laboratories from other countries, including Jülich Supercomputing Center, CEA in France. It includes CDAC in India. It also includes the University of Oregon, which contributes the E4S software to the High Performance Software Foundation. You can learn more about it at hpsf.io. You can see other vendors that have participated in this, including AWS, AMD, Intel, NVIDIA. And the Exascale Computing project had three different focus areas. There was the application development, the software technology, and the hardware and integration. There were over 70 unique products that came out of the software technology of Exascale Computing project. And this is the roadmap to Exascale systems. And I understand that there is a lot of interest in Exascale computing, even in other countries, and they are all developing large-scale supercomputers. In the US, we used to have supercomputers based on only NVIDIA GPUs until recently, and that has evolved now into supercomputers from three different vendors, including NVIDIA, AMD, and Intel. And there are systems such as Frontier, which is the #1 system on the top 500 list, and El Capitan, which has now become the latest #1 system on the top 500 list. They are located at Lawrence Livermore National Labs and Oak Ridge National Labs. And Argonne is is hosting the third largest supercomputer, the Aurora system. So our goal is to build a comprehensive, coherent software stack and prepare for massive on-node parallelism with GPUs on these supercomputers. And the Extreme Scale Scientific Software Stack, or E4S project, helps to deliver such a modular, interoperable, and deployable software stack. And it includes tools such as Tau for measuring and optimizing the workloads. Now, we have support for E4S on commercial cloud platforms, and we have ported E4S to different cloud vendors. And it is now known as Paratools Pro for E4S from my company Paratools Inc. And you can learn more about it at paratoolspro.com. Now, this E4S stack is a community effort. E4S is a community effort to provide open source software packages for developing, deploying, and running these codes on HPC platforms. And it's a curated software stack based on the SPAC package manager that originally came from Lawrence Livermore National Labs. It's part of the High Performance Software Foundation, part of the Linux Foundation now. and it enables application developers to be more productive. I've got over 100 different HPC applications, including tools that you may already be using, tools like OpenFOAM for CFD, GROMACS, NEC 5000, LAMPS, even electronic design automation applications like Zeiss, which is a circuit simulator compatible with the SPICE circuit simulator, and a number of different AI/ML packages, including TensorFlow, PyTorch, TorchBraid, Scikit-learn, Pandas, JAX, Horoward, LBAN, all of these optimized for GPUs. GPUs not just from NVIDIA, but also NVIDIA, AMD, and Intel. You know how hard it is to develop applications. You know how hard it is to install these applications. We have a solution that integrates software that targets different GPUs. And we have container images. These are available on Docker Hub with Docker containers. We have Singularity containers that you can download. And we also have tools to help you use base container images and customize them for your own application needs. We have support through ParaToolSync, and we are partnering with Adaptive Computing and their on-demand data center ODDC product with ParaTools Pro for E4S with support for different cloud providers. There are other tools that can be used to chain to SPAC instances, so you can customize and tweak the software so that you can create custom software environments for each user. We have tools to launch containers that can replace MPI with the system MPI to get very good performance with containers. We even have tools to create custom containers using the base image, where you can use a tool called E4S a la carte or ALC to customize the images, where you say, start with this base image, add these additional packages, and create a new image. Well, what are containers? Containers are just a lightweight collection of executable software that encapsulates everything that you need to run a specific task. And you may have seen systems with hypervisors. Here is a hypervisor which is running a virtual machine with its second operating system over here, where you see there is one operating system here and there's a second operating system within a VM, or a container where there is an operating system on the host and there is no OS kernel running inside the container. It uses the kernel from the base operating system, and it's more efficient than the VM approach. And we have a large number of containers. The latest release of E4S was on November 15th, and it includes 132 different packages. It also includes tools like NVIDIA's NeMo. We have Hugging Face, Hub, Deep Hyper, Gemini API, OpenAI, TorchBraid, Pandas, and all of these tools with support for new architectures, including AMD MI300A and 300X. And we hope to provide better commitment to software quality. We have a doc portal, quarterly releases, and build caches that can help you improve your installation times. And then you can see that starting with our first release in 2018, we now have 132 full products, where we started with 24. You can download these containers from the e4s.io page. Just click on the download button, and then you can get the CUDA container or the Intel or AMD containers for different architectures. These are the products that are in the image. You can see tools like GROMACS, HDF5, Cocos, Tau, Pappy, Prilinos, and a number of different languages such as Chapel, Rust, Julia with support for MPI, Python, and AI products like NVIDIA NeMo, TensorBraid, Deep Hyper, OpenAI, TensorFlow, PyTorch, all optimized for GPUs and even 3D visualization tools like these. You can chain multiple SPAC instances, create custom environments, install packages that are not there like Valgrind. These are some of the tools that are available. Those who are using Python and AI will see that just launching this container with CUDA 90 on a H100 system, I can import Nemo, OpenAI, Google Generative AI or Gemini, TensorFlow, PyTorch, Hugging Face, JAX, DeepHyper, Pandas, OpenCV, Scikit-learn, Open3D, and other commonly used Python tools. And all of these packages are included in this container image that you can simply download for free and use and build your own platforms using this base platform of E4S. So this can accelerate your development to go to the custom environments on HPC machines. You also have support for cloud platforms and support for GPUs. You can see all of these packages installed with support for CUDA. And there's 170 different packages installed in this image. This is on a Grace Hopper system. You can see the CUDA 90 with ARM64. You can see the different products that are available. You can search for these on the doc portal, and they'll rake the repos every night and then get you the latest information about the products, and you can go to their webpage. Here is an example of a NWChem, a tool that's included in our image. And the container launch tool from E4S is a tool to simplify the launch and substitution of the MPI library. So you can build your application using a container from E4S and then launch it on the system and replace the MPI. Now, if I take a step back and I say, what exactly does this help me? Well, this helps you distribute MPI applications in a binary form with the container. Until now, we were forced to distribute our MPI applications in source form. This allows you to distribute them as binaries with the container and still get the best performance by substituting the MPI in the containerized application binary with the system MPI. So if you are running on a HPE Cray system, you can use the Cray mpitch library and substitute it. We can do substitutions with the mpitch ABI, such as Intel MPI or MVAPitch, or also OpenMPI, which has a different application binary interface. So you can launch a container with this, just specifying what kind of a backend you need, like Singularity, where is the image, and then bootstrap it in this manner where you say, these are the commands used when you start up the container. And then simply launch your MPI job with E4SCL, prefixing the MPI run command. There are some community policies for inclusion of a product in E4S to improve the quality of the software. You can have a look at these policies on the web page. And we use the SPAC package manager for software delivery. And SPAC is used for a large collection of tools. And it's very hard to manually install over 100 different packages. So if you see the top level red boxes in this dependency graph, you can see that in this software stack, to install 100 packages, you need 600 additional packages to support that. You can simply clone the SPAC repo and get the environment, find the compilers, and then external tools like AC local or M4, and then simply install tau, like saying SPAC install tau with an @ symbol for a custom version, where you can say SPAC install tau version 2.34 with GCC. GCC is specified with the percentage symbol. This is a compiler that is found when I say SPAC compiler find, and it's saying, please use GCC version 11.20 with SPAC. with variants of the tau recipe. So you can say with MPI, with Python, with pthreads, you can specify an MPI such as mvapitch 2 version 2.3 and give other custom variants of the particular package. Plus is for enabling an option, tilde is to disable an option. And there are over 7,000 different tools integrated in SPAC. You can visit the spac.io package manager website and learn more about it. Now we have taken E4S and then we have ported it to the cloud platforms, commercial cloud providers. We have an image called ParaTools Pro for E4S. Now you may be wondering, as I move my workloads to the cloud, which cloud provider should I go with? Should I use AWS? Should I use Oracle Cloud Infrastructure? Should I use the Google Cloud? Or do I use the Microsoft Azure? Well, why not all of them? Well, what are these cloud providers providing? Each of them have different network interfaces. Our HPC and AI workloads need low latency, high bandwidth. We need a remote desktop accelerated by a GPU. We need integration with batch schedulers such as Slurm or Torque. You may be wondering which image to start with. If you just start with the base Ubuntu image, it is too steep a learning curve. So you need a better starting point which will work across different cloud providers to avoid a vendor lock-in. And command line interfaces to launch these cloud workloads can be very cumbersome to use. You can also think of bursting to the cloud from on-prem clusters. The key things to worry about are which MPI do I use? We have chosen mvapitch as the MPI because it works efficiently across different network adapters provided by these cloud providers. AWS has the Elastic Fabric adapter, Microsoft Azure has InfiniBand, OCI needs ConnectX, and Google uses IPUs. Even within the node, you need support for XPMEM drivers. We have support for GPU direct async, and we are building with mvapitch Plus on all these different cloud providers using the adaptive computing's ODDC interface to launch jobs. Now, what ODDC provides us from adaptive computing is a uniform way to target multiple cloud platforms with a common image. This image is now available in the marketplaces for the different cloud providers, and you can start with this image to build your solutions. This is a listing of ParaTools Pro for E4S on AWS. This is work that was supported by the Department of Energy's Small Business Innovation Research grants for phase 1 and phase 2. And we thank them for their support. Which supports Slurm as well as Torque. It supports PCS or parallel computing system as well as the parallel cluster from AWS. It supports Torque with ODDC, and it's a commercial image with support. We also have the same image available now on Google Cloud, and it comes with a 28-day free trial, and then after that you have to pay by the hour. So it's like 99 cents per node hour. What I mean by that is if you have a deployment on a system with multiple H100 GPUs and say 8 H100 GPU node costs $104 per node hour, then instead of $104, you would pay $104.99. So there's an additional 99 cents per node hour that you will pay to use the image, but then it will provide a lot of features that you're looking for. This is the listing of the same image on Azure Marketplace, and we are working on OCI. What ODDC allows me to do is configure clusters where I can pick the head node, I can pick the compute nodes, and then I can launch this. I have a demo here at paratools.adaptivecomputing.com. You can also If you are interested in checking this out, go to this website. You just have to click this training session, enter your email name and a session code, which is 19675. With this session code, you can launch and run a cluster with a remote desktop on Microsoft Azure. Here with this 19675 at paratools.adaptivecomputing.com, you can simply click over here, and this is one of the fastest ways to get onto a remote desktop environment by opening a VNC viewer, allow the pop-ups, and then you'll get a remote desktop. You can click the 9 dots here, open up a terminal window, open up Firefox. You can launch the SPAC command and see which packages are installed. You can launch Visit, ParaView, launch it like this, open up a file, look at examples, open this up, add a pseudo color, say pressure, and rotate a cube like this. We also have a lot of E4S containers. You can start with a base image. You can customize it with these tools and launch it with E4S CL within the cloud image. And then we have releases of these tools too. So here are some examples of using the tools. Here is a containers example. And you can use your own AWS credentials or credentials from other cloud vendors. You can go to this marketplace, search for the ParaTools Pro image. You can click on this image, subscribe to it. You can go to Adaptive Computing and even start your free trial for E4S, and then configure your own clusters with your own credentials and say, customize it using this upload script where you can specify what it needs to do. You can deploy a cluster, and then you can be productive on the cloud. So in conclusion, I would like to say that using the E4S platform with containers, cloud, bare metal can save you enormous amount of time as you explore high performance computing, as you explore supercomputing environments. You can run on commercial cloud platforms like AWS, GCP, Azure, OCI. There are opportunities to build custom solutions on this ParaTools Pro for E4S platform, along with Adaptive Computing's ODDC. There are also opportunities to co-sell this and sell this image to other customers and retain a percentage of the additional cost that the users pay. So there may be ways to bootstrap this and partner with us and build a custom solution in regional markets. And you can learn more about it at paratoolspro.com. A lot of the work goes on at the Performance Research Lab at the University of Oregon in Eugene. And I would like to thank our sponsors from DOE, DOD, NSF, NASA, our industry partners, CEA in France, and our partners from other institutions. This is work supported by the US Department of Energy Office of Science through the PESO project. It's supported by HPSF and SBIR and the Exascale Computing Project. So with this, I would like to show you a quick demo of how it works. And some of you may be interested in trying this. And let me just point out that there is a session code as you go to paratools.adaptivecomputing.com 19675. So how does that work? Let me just start from a new private window. I'm going to this website, paratools.adaptivecomputing.com, and I'll go to this training session. I'll put in my name, my email address, and this code, which is 19675. Okay, and then I click this register button, and it takes me over here. It may prompt me to pick from different clusters. Here is a cluster on Azure. There are 2 nodes in the cluster. I'm deploying it by just clicking this VNC viewer. I click here, it will say pop-up was blocked. I click on the pop-up, allow this pop-up, and then I have a remote desktop. A remote desktop where I can say, go to an example like this. I can say, show me MPI proc name .c. This is an MPI program. I can compile it using the MPICC. I have an executable. I can run this using MPI proc name.qsub or the torque scheduler and say qsub MPI proc name.qsub, just like I would with any other cluster. I can also run this on the login node, although it's not recommended. And it's showing me, the login node does not have the InfiniBand connector. But if I say qstat -u, then it shows me that this job completed. It ran on 4 nodes, and here is the output file. And you can then see the output over here. This is this job number ending in 3. And here is the output. So I can then look at this. See, this is running on 0, 1 and 0, 0, 2 different nodes connected by InfiniBand. If I want to see what is the speed of the network interconnect and what is the peak speed. So InfiniBand adapters typically have a peak speed of 200 gigabits per second. So if I look at the OSU benchmark, I can say over here, I say qsub bandwidth.qsub, and I'm launching this job on 2 nodes and then trying to measure how much time it takes to transfer the messages of different sizes. And how close do I get to 200 Gbps, which is what I typically use in the on-prem clusters. So here, this job is queued, and I can check the status of this job like this. And then I can compile codes. I can see what packages are available. Here is spac find -x, all of these packages, spac find -x with plus CUDA. And you can see what packages were installed with CUDA. And now this job has completed. If I look at the output, there is this output from this job. And I'm trying to find out how good is the MPI library? What is the peak on this system? It's 200 Gbps, right? And I see the megabytes per second for a message of this size is 24,000 megabytes per second. And by megabits per second, I multiplied by 8, and I get 197 gigabits per second. So out of 200 theoretical max gigabits per second between the 2 Azure nodes, I'm getting 197 gigabits per second realized at the application level with MPI. So this is spectacular performance that we can see. I can say cat latency.qsub, and then qstat this, and it's queued. It will run this, and I'll be able to see what is the latency between the nodes. Is it less than 10 microseconds for sending a message between the 2 nodes? Because when we build applications, HPC applications, AI applications, latency and bandwidth are really key on large-scale clusters. So this image provides you 197 Gbps between the nodes. And if I look at the job, it is completed now. And here is the latency. And I'm getting 1.9 microseconds latency between the 2 nodes. So It's a very low latency, high bandwidth interconnect. And I have a remote desktop. So if I launch a GUI tool like Visit, I can run this tool. I can open a terminal, open a window, open this. I can access this GUI. I say pseudo color pressure. This is all happening on the Microsoft Azure cloud. I click draw, and here is the window that I can rotate this image in real time, all on the web. Let me try to slice and dice this data. I say slicing, ISO surface, draw this, and you can see the results. We also have NVIDIA NeMo, we have Jupyter notebooks, we have other environments. This is the MPI proc name example. I can say Codium, MPI proc name.c. And this is the Visual Studio environment where I can build applications, run them, start a new terminal, debug them, all from within Visual Studio's equivalent product called Codium. This is MIT licensed, and you can see the syntax highlighting over here. You can launch Jupyter notebooks. You can launch other visualization tools. And here is an example of Tau, and I can launch. Here is a demo. Now, if I wanted to use Python products, I can even install additional packages. In this case, I was just trying to install the Penny Lane, and Penny Lane is of course not available in the image, but I can just say pip install Penny Lane, and here I can import this image, and you can see this. Now here is Tau's Paraprof visualizer. You can see the results. You can also go to see the 3D visualization provided by Tau. And here is the bar plot that I showed earlier. And you can rotate this in real time and look at the function and thread sliders like this. And go here. And you can see over here where the bars intersect, how much time was being spent in that function. You can zoom in, zoom out. You can see the shape of the execution with Tau. You can see scatter plots where here we see for a given function, minima to maxima, and each rank is a blue ball or a red ball. And there's one CPU that processes the central axis of the tokamak reactor where it is red hot. And so you can see the scatter plots. And if you would like to try this image and try the Python tool, all you have to do is go to this website and launch this image. To go to paratools.adaptivecomputing.com and go to the training session, put this 19675 as the session code and give your name and login, and you can try this. So multi-user, multi-GPU, multi-node environment on the clouds with really fast 197 Gbps between the two nodes, low latency interconnects, and the full software stack is available. So with this, I will end my talk and take some questions.
Any questions? Audience, any question?
Any questions from the audience?
Sir, I have a question, sir.
Yes, of course.
How can the Tau helps in identifying if there is a bottleneck?
So Tau has instrumentation hooks into different libraries, and you can measure the time spent in different code regions. And there are some routines, synchronization routines that are bottlenecks that are clearly identified in Tau. And you can see the time spent in those barrier calls. You can see the time spent in scheduling threads. You can see detailed information with no change to your application source code, no change to your application build system or the binary. Simply launch it with the Tau exec tool, and it will show you how much time is being spent in different code regions, and then visualize it using Paraprof.
Okay. Sir, when we are basically configuring the Tau, so in that case, some challenges are faced. If there is some challenges, what are the challenges faced?
So you can use the SPAC package manager to install Tau. That makes it very easy. You can just clone the SPAC package manager. You can just say SPAC install Tau, and it will install it and take care of all the installation headache. We are using SPAC internally to install Tau on our cloud image over here. So for instance, if I go to this terminal and I say SPAC find Tau, it shows me that there is a Tau installation. I can see how Tau was configured, what are the dependent packages like PDT, Python, mvaph that it's using internally, and how it built it with which options, like with binutils, with libunwind, with libdwarf. All of those things can be done very easily by just saying SPAC install Tau, like that. Does that help you?
Yes, sir. Yes, sir.
And if you are using our image on the AWS or Azure or one of these cloud providers, you'll see that Tau is already installed in this image. You have a very performant desktop. You can launch GUI tools. You can launch your web browsers. You can have a remote desktop with all the tools and then run your jobs on the compute nodes. And multiple users can do that in their own environment that they can customize.
Okay. Any more questions from audience?
I have a question. Like, while you are discussing, that is basically primarily the processor part and the cloud model of the memory. So, like, does it have any mechanism to control the memory also, or that is only
Absolutely. So you can set environment variables. There's a lot of environment variables that we have in Tau when you launch your application. And you can see that there are some settings to track memory. So for instance, you see over here, there's a Tau track memory footprint. If you set it to 1 and run your application with say MPI and Tau exec, it will track the total memory usage and show you the high water mark. You can see other memory debugging features of Tau for even doing memory debugging and seeing where there are problems with your application. You can also use Tau exec -memory option to check the bounds. Does that help answer the question?
Any more questions from the audience?
Well, this is an interesting platform. Instead of starting from a scratch and then trying to build all the tools yourself for an HPC environment, I would recommend that you start with this paratoolspro.com image and then build your custom solutions based on that image.
Okay. Sir, thank you for your informative session. Sir, my sincere apology to you, sir, and to one and all present here, because I had a glitch on accessing the microphone from the browser. I never have able to introduce you, sir. But maybe the end of the session, I'd like to share a brief on you, sir.
Absolutely, go ahead.
The Professor Samir Shinde, sir, serves as a research professor and the director of Performance Research Laboratory at University of Oregon, and the president and director of Paratools Inc. USA and Paratool SAS France. He serves as the lead developer of the extreme scale scientific software stack E4S, Tau Performance System, Program Database Toolkit, and HPC Linux. His research interests include scientific software stacks, performance instrumentation, compiler optimization, measurement, and analysis tools for HPC. He served as the general co-chair for ICPP 2021 and is serving as the general co-chair of EuroPAR 24. He was the vice chair for technical papers for SC22 and has served as the chair of performance measurement, modeling and tools track at SC17 conference and is serving as the track chair for programming environments and system software track at ISC25. Finally, he has received his BTech in electrical engineering from IIT Bombay in 1991 and his MS and PhD in computer and information science from University of Oregon in 1996 and 2001 respectively. Once again, sir, we're enlightened to have you in between us, and we had learned a thorough knowledge about the Tau performance system, its tracking on Python, the different threading concepts, the paraprof 3D visualization, HPSF, and a lots of things, and a live demo about the supercomputing environment. So, in and all, we have enriched with sir's informative session. So now I'd like to ask our principal, sir, Professor Dr. Dhrubasish Sarkar, sir, to say a few words about sir.
Thank
Sir,
you.
what do you?
Sincere thanks and regards to Professor Samir Shende for such a session. And I think many of the Professor Shende, you will be happy to know that 60 plus institutions and organizations across the country and total 170 plus participants are attending your session right now. And for the participants, Professor Shende is taking the session from 6 a.m. early in the morning. So our sincere gratitude to you, not only for this session since last 2020 possibly, the last 5 years you are like basically supporting me, helping me in many ways. So our sincere regards, and I'm sure very soon we will meet. Anytime you visit Kolkata, then invitation from Supreme Knowledge Foundation to you, and definitely we'll coordinate, and we want you to see you in our campus. Our sincere regards.
Thank you very much. Thank you for inviting me. Appreciate all your support. Bye.
Okay. And one more request, if your slide can be shared so that we can share it with the attendees.
Oh, absolutely. I have sent it to you by email.
Yes, for your session, I have already shared, right? Sorry, yes.
Yes, so please go ahead and share it with the participants.
Yes.
And if they have any other questions offline, they should feel free to reach out to me. And here is my email address, samir@uoregon.edu, that you can send me a note and I can chat with you offline.
For all the attendees, Professor Shende is always extending his utmost help in every aspect of academics and other collaboration. That I know. So you can definitely reach him. He will try his level best to support.
Sounds good. Thank you very much.
Thank you, sir.
Okay.
Okay.
Bye.
Thank you. Thank you, sir. Okay. So,
Thanks, sir.
okay. So we come to an end of the second day of 6-day ATAL online FDP on building the next wave of Indian startups with advanced computing technologies. Now, as just yesterday, today we had two interesting and very informative sessions by our two renowned and eminent speakers, Professor Dr. Debashish Dev from MECOUT and Professor Dr. Samit Shende from University of Oregon, USA. Now, Professor Debashish Dev spoke about quantum computing and how it is having impact on various industries. And Professor Samit Shinde, sir, he spoke about how supercomputing is accelerating research and development for startups. Both the sessions were really interesting. I hope the participants have really enjoyed it. I'm really thankful to both the speakers who, despite having such a busy schedule, they have come to share their expertise with all of us, with all the participants. We are really thankful and grateful to both them eminent speakers. And we are also, and finally, thanks to the participants who have attentively listened to this. And both the sessions were really very interesting, as well as it was interacting. We got good number of questions, question answer sessions as well. So thank you, participants. Now, as we come to the end of this day, we have shared one feedback form for today, just like yesterday. So today also it is, I request all the participants to please fill up this feedback form. Okay, it is important. Now, tomorrow, this is not the end. This is just the second day. Tomorrow, we have another two interesting sessions by Professor Dr. Bimal Kumar Roy. He is a retired professor and former director, ISI Kolkata, who will speak on the opportunities and challenges in AI and startup ecosystem, and followed by another important session by Dr. Munmun Das from Accenture, who will enlighten us on building scalable AI solutions for startups. So these are the two sessions we will have for tomorrow. So I'm expecting that participants, just as today we had a very good response, you listened very attentively in the same way, and we are expecting that tomorrow also you will join both the sessions and get benefited from these sessions. So we are coming to the end of the sessions. Now, if we have the permission, with permission from our coordinator, Subroto sir, and from our principal sir, Debashish sir, if they permit, I can declare this day both the sessions closed and call it a day. So sir, shall we then end this day? Okay, we have. So, sir, we are coming to an end of this day. Okay, so we are closing the session. So, feedback link has been provided in the WhatsApp group. All of you, please do fill it. Okay, so good night, all of you. Tomorrow we'll meet again. Okay, thank you, all of you. So, we are.
Thank you, sir. Sessions.
Okay. Thanks to all the participants. So tomorrow we'll be meeting again.
Thank you, sir. Good night.
Yes, good night, all of you.